Hey guys, today we're going to be talking about center of mass and moment of inertia. The problem we're going to be doing is focusing on a golf club that has been simplified so that we have at the very end, we have some sort of point mass, which is the end of our driver. And then we have that point mass attached to our overall golf club. I guess we can give it a bit of a handle here. So we've got our overall golf club like that. We are told that our point mass is right here. It is the head of our driver. It has a mass of 0.25 kilograms. And then we have our overall handle, which is being simplified to be treated as a rod. And it has a mass of 0.05 kilograms. This entire thing is being rotated not around the end of the club, but around your shoulder as you're swinging the club. So we're saying that it is a rotation about some center of rotation out here. And we'll say that it is spinning downwards here in order to hit our piece. And we have been given the information that the end of the club is 1 meter away from the center of rotation. And then our overall piece, I don't think I have space above. Probably should have thought about that earlier. Our overall club length is 1 meter long. So that means that if we wanted to look at our forces here, we are going to have a point mass force, which is mg acting over here. And then we have a force for the rod. We're going to have that happen at the center of the rod, which is going to be right here. So this would be at 1/2 meter. Do I have space? I do have space. 0.5 meters. And we have an mg here. Because we can say that we're being told it's a uniform rod, meaning that the center of mass is where we can apply it. And then we are told that the golfer is actually providing a force. And that should draw it above here, but don't have space. Maybe I do. Golfer is providing a force here, so this is the force of the swing. I don't have space to label above, that's for sure. And it's still not quite on it. Close enough, though. We've got a force of the swing, and the force is 20 newtons on that in order to get it to go through the swing. With that, we are asked for a handful of items, so we're going to go ahead and list them all out right here, or what to finds. And with that, we are asked for the center of mass. We are asked for the torque provided. We are asked for the moment of inertia. We are asked for the angular acceleration. And we are asked for the velocity at 90 degrees. And just to be clear, this center of mass is going to be x center of mass. The position where our center of mass is. Torque is our torque of the person, torque golfer. We have our moment of inertia, which is just going to be I. We have our angular acceleration, which is going to be alpha, and then we have the velocity at 90 degrees, which we are just after the linear velocity v. How fast is the head going at the point where it's going to make contact with our stick? With this, we can just start going down our list. So the first thing we have is we have our center of mass. So, oops, wrong pen. We know that our center of mass is going to be equal to the sum of the position of all of our center of masses of all our different pieces times the mass of all of those pieces, all that divided by the total mass, so the sum of all of the individual masses. It's the average position going on here. So with that, we have two masses, and we're going to set this up as what is the center of mass as compared to this being x equals 0. So, and we're going to say positive x direction is to the left here. So with that, our x center of mass is going to be equal to our first piece. We have, let's do the end of the club because that's easy. We're going to have our mass of 0.25 kilograms. And we have our distance between here and here, that's 1 meter plus 1 meter, is going to be 2 meters. Okay. And then our second piece is going to be the overall club. It is a linear piece, and we're assuming that it is averaged out. So the center of mass for just this linear piece is going to be halfway within this 1 meter length. So the mass is 0.05 kilograms. And that means, and that 0.05 is acting at 1 meter plus half a meter because the center of this is at 1/2 meter. So 0.5 meters. And then divide by the total mass, that's the 0.25 kilograms plus 0.05 kilograms. And that should come out to a total of, where do I have it here? 1.7 meters. So our center of mass is 1.7 meters from here. So this is 1.5. It would be something right here. That is the location of our center of mass of our overall club. So this guy is 1.7 meters. Okay. With that, on to our next piece. How much torque are we providing? This one should be review. So we have torque. So our torque is going to be our force perpendicular to radius. So our force is 20 newtons. And we are currently acting straight down, which our rotation, our radius is given as this distance, and that is 1.2 meters. I think I forgot to write that one, 1.2 meters. Write that one down, but that force is perpendicular to our radius line, so we don't have to worry about any sine or cosine action. So we can just write it as 20 newtons. We don't need anything more, and our radius is 1.2 meters. Okay, and with that, that is going to end up giving me 24 Newton meters, which is my torque. 24 Newton meters. Now that is just the torque of the golfer. Ooh, that looks like torque of gravity. That is torque of the golfer. So torque of the golfer is 24 Newton meters. Simple enough. That one should have been review from stuff we've already been doing in class. Next piece that we have is finding our total moment of inertia. So our total moment of inertia, we're going to have to add together the moment of inertia for our overall club as well as our point mass. Let's start with the easy one. We have the moment of inertia of our point mass. So that is going to simply be moment of inertia of a point mass. So this is moment of inertia of the head is going to be mass times the radius squared. The mass of our head is 0.25 kilograms. Our radius for the head is 2 meters away from our center of rotation, so that is 2 meters. And that 2 meters needs to be squared. So 2 squared is 4 times 0.25 should come out to 1, and it is 1 kilogram meter squared. That is the moment of inertia of the head of our piece. Our next piece is going to be looking at our club. So how we're going to do this, we have the moment of inertia of a rod rotating around the center was given to you. We have the moment of inertia of a rod rotating around the end. We do not have the moment of inertia of a rod rotating slightly off the end. However, since these things add together, we can figure out the moment of inertia of a continuous rod and subtract the moment of inertia of the point of the half that we are working with so far. So, I don't know, we'll call it moment of inertia supershaft. So, with that, we have our moment of inertia of a rod is 1/12 mr squared. And actually, let's do this all at once. Let's just say moment of inertia of our shaft. So we got 1/12 mr squared minus the 1/12 mr squared of the shaft that is not actually there. So this guy is total length. This guy is subtracting the missing portion. Okay. With this, if we were twice as long, since our mass is consistent, our mass is going to be twice as much. So we're going to have 1/12, and we're going to have twice our original mass, so 0.1 kilograms. That's double our 0.05. And our total radius for this is 2 meters, and that is squared. Now subtracting the portion, so 1/12, the mass of this is going to be the difference between our fake total mass, which was 0.1, and the mass of the end, so that's going to be 0.05 kilograms. And that is going to be multiplied by the radius of this fake piece. So I'm going to draw in this fake piece that we're subtracting right here. We basically extended our shaft all the way up to the shoulder, and we are now removing that portion because that is not part of what we are considering. So with that, that is a radius of 1 meter squared. And you notice that if I just put in 1 meter and I said that was this, 1 meter squared is 1, 2 meters squared is 4. Currently I'm getting 3. If I just did this, ignoring that, it would get 1. I would get the wrong answer. But with this, what I do get for my total moment of inertia is going to, for my total moment of inertia of my shaft is going to be 0.03 kilogram meter squared. And that means that my I total is going to be the moment of inertia of the shaft plus the moment of inertia of the head. So that is 1 kilogram meters squared, that's right there, plus 0.03 kilogram meter squared, and that is going to give me 1.03 kilogram meter squared. And with that, we're almost there. Okay. With this, we have been told that we're going to ignore the torque caused by these the gravity of the club. That's just because we're talking about a full 90-degree swing, and that 90-degree swing, well, the portion of this that's perpendicular is going to change, because if initially I've got my club like so, I've got 2 pieces, and at this point my torque from each of those is perpendicular, so it's just going to be the force times the radius. When I get to here, they are no longer perpendicular, so I'm going to have some sine and cosine aspects going in there, sine or cosine, I guess, depending on how you set up your angle. And then when I'm ready to hit the ball, the gravitational portions of these are 0. So this is 0, this is going to be mg cosine of some theta, and this is mg. And I would have to go through and keep track of each incremental little bit and how that impacts throughout my entire swing. So we have been told, ignore this. So we are just going to go ahead and leave that out for this portion of the calculation. If you wanted to do it correctly, you'd have some calculus in here, and you would have a changing impact of torque, a changing torque that is acting on the club due to gravity, caused by gravity, throughout this. So we've been told, nope, we're not doing that because we don't have the resources for it. We're just going to look at it as it is. So torque with our equation, so sum of our torques is going to be equal to I alpha. Since we're moving, since we're accelerating, alpha is not 0, so we can't use the assumptions that we made from the last class period. So we have our torques, and our only torque is this torque caused by our, well, not quite on the board there, our force right here. So that is going to be, you know what, we'll call it torque of the golfer. I'll write out golfer just because it is not the torque caused by gravity. And that is going to be our moment of inertia of our club times our angular acceleration of our club. So how fast is our swing picking up speed? And with that, we don't have anything going on with the mass. So I'm just even going to write it here. Ignore mass. Oh, yeah, let's ignore, we'll call it ignore gravity. For this problem, just to make it solvable for us. So with this, our torque of our golfer, caused by our golfer, is 24 Newton meters. And that is going to be equal to our moment of inertia of the club, which is going to be 1.03 kilogram meter squared times my angular acceleration. And I can solve for my angular acceleration, which is going to be that 24 Newton meters divided by 1.03 kilogram meter squared. A Newton is a kilogram meter per second squared. So I have a Newton meter, so I've got times meter, and I'm dividing that by kilogram per meter squared. Kilograms drop out, meters squared drop out. I get 1 over time or seconds squared. Well, if we think about our units of alpha, alpha is going to be radians per second squared, and we talked about how radians just don't show up with our units normally. So there we are. So we've got 24 divided by 1.03. That gives me 23.3 radians per second squared. So that is my angular acceleration. That is my angular acceleration caused only by the torque caused by the golfer. Sorry, standing in behind that one. Now, if I wanted to, I could figure out, well, what is my torque at the very top? So I could, what is my my instantaneous angular acceleration when I am horizontal, in which case I would add the torque of gravity of the shaft, and I would add my torque caused by gravity of the head, and that would basically add this guy, the shaft would be mass of the shaft. So mass of the shaft would be 0.05 times 1.5, because that's the radius. So mass times radius, and we're perpendicular there. And then this guy is going to be 0.25 times 2. Our mass, both of these times 9.81 times 9.81. So this guy is going to be half of 9.81, which is going to be 4.905. This guy is going to be very small. So 0.05. So that's 0.075 times 9.81. That is going to be slightly less than 0.75. It's going to be smaller than 3/4. So the shaft, not really big compared to the 24. The head probably is impacting that, but that's only at the very top of the swing. When we get to horizontal, it's 0, so averaging out maybe half of that, it is going to impact it, and it should be considered. We are just not considering it because of the type of question that we're asking for. And I will tell you whether or not I want it to be considered. The big deal is whether it is an instantaneous question or a over time question, because we can solve it instantaneous. We just showed that we could. For a longer question, that becomes a bigger issue. Okay, last piece is our velocity at 90 degrees. At this point, we are already, we're through everything new. So we want velocity at 90 degrees. Let's go ahead and start by first finding our rotational velocity at 90 degrees. So with this, we can go ahead and we can go back to our kinematic equations, in specific our rotational kinematic equations. The easiest one to do here is going to be our fancy one. Our omega at time 2 squared is going to be our omega at time 1 squared plus 2 times our angular acceleration times our theta at 2 minus our theta at 1. And if we think back, this is the equivalent of when we had our v2 squared is equal to v1 squared plus 2 times acceleration times x2 minus x1. Just switched into the rotational domain. So we want our velocity at 2. So we want omega 2 squared. Omega 1 squared, well, this guy, we're starting horizontal and we're starting to move at that point, so that is 0. Our angular acceleration we just solved for, so that's 23.3 radians per second squared. Our thetas are 90 minus 0, except that is in degrees. We want it in radians to make sure everything is consistent. 360 degrees is 2 pi radians. 180 degrees is then pi radians, because that's half of it. And half of that would be pi over 2 radians for 90 degrees. And 0 degrees is 0 radians. So this is radians. So my omega 2 is going to be equal to the square root of 2 times 23.3 radians per second squared times pi over 2 radians. I end up with radians squared per second squared. Square root is radians per second. And I get a omega at the end of 8.56 radians per second. Perfect. And then with that, in order to get between rotational velocity and linear velocity, we know that velocity is r omega, r radius times omega. In this case, we want the velocity of the end of the club. So our radius is 2 meters. So we have 2 meters times 8.56, 1 over seconds. Our radians just kind of disappear here because this is a conversion, meters per radian, you could think of. Or you can just remember that the radians don't really show up as units normally. So this comes out to 17.1 meters per second. Now remember that the correct answer for this is actually going to be larger because we have these gravitational portions that are going to help us swing our club faster. That's going to increase the angular acceleration. Again, we just didn't include it because it would require us to calculate at each instantaneous point because we would have a changing acceleration. And right from the start, when we talked about acceleration in kinematics, we said that for this non-calculus based class, we are always going to have a constant or a 0 acceleration. So don't worry about it. It's covered. That's all you need to know. That's all you need to know. If we have questions like this, it will be set up in such a way that you can ignore that for those questions. Hopefully that was helpful. Take care.